trees, roads, buildings, other houses, other buildings, uh, and stuff like that. So these are different geographic phenomena. We will take a slice of reality, or we will collect some data from the real world and bring it in the GIS world. In the GIS world, this data is converted into a computer representation. And using this representation, we do further computing like spatial analysis, or we create visualizations. This entire science is called geoinformation science, or in short, the GIS world. Now let's understand, for those who are not GIS or the geography background, you need to understand what do we mean when I say geographic phenomena. Geographic phenomena are the study of objects of a GIS. What are the objects that can be represented inside a GIS? So if you look at the image on the right, a very nice scenery of the sun going down, there are so many different phenomena that you can see. Some of them you can feel, some of them you can see. For example, things you can see are water, land, rocks, soil type, and also the slope of the land or the elevation of the land. Some things that you cannot see but are still there are things like air temperature, water temperature, air pressure, and so on. So, geographic phenomena is everything that exists in the real world. Everything you see outside is geographic phenomena. And we will see how we can take slices of this and represent it inside GIS. Geographic phenomena also has a formal definition. The definition goes like this: a geographic phenomena or phenomenon is a manifestation of an entity or process of interest that can be named, one. Two, it can be georeferenced. What is georeferenced? That is, it can be assigned a location. It can be given a latitude and a longitude. And thirdly, and optionally, it can be assigned a time at which it was present. For example, this is a screenshot from Google Maps, and here you can see this T-shaped building, which we call it as the IIRS main building. This is where most of the departments, academic departments, are there. So this building has a name, the IIRS main building. That is point number one. It can be given a location, it can be given a latitude and a longitude. So that gives me point two. Therefore, this phenomena, the IIRS main building, is a geographic phenomenon. So anything that you see outside which can be given a name and which can be georeferenced is a geographic phenomenon. Optionally, it can have several attributes. For example, when was it established? When was this institute established? In 1966. What are the current number of departments? It is 10. Number of faculty, number of students, and so on. It can have n number of different other attributes. The word that I use is attributes. So any phenomena which has these two basic things, that is a description or a name and a location, can be represented in GIS. Optionally, it can have any more number of attributes. Now we go deeper into geographic phenomena. There are two types of geographic phenomena. First is called a geographic field. The second one is called a geographic object. Now, how do we differentiate a phenomena, whether it is field or whether it is object? So a geographic field is a geographic phenomenon for which, for every point in the study area, a value can be determined. Now, for example, let me skip to the next slide and then I'll come back to this again. Now, if you look at our earlier image, imagine you are looking from the top and this is your study area. You can see rocks, you can see water, land, and then there are things like temperature, pressure, elevation. These are the different and many more things happening in this scene. Now, which phenomena is available at each and every point in the study area? Which phenomena are available at each and every point in the study area? For example, let's take temperature. So yes, temperature is there everywhere. You can take a thermometer or some other instrument and measure the temperature at every point in the study area. Same is the case with air pressure. Same is the case with elevation. So at every point in the study area, a singular value can be determined. That such phenomena would be called as geographic phenomena. These three are classical examples of geographic fields: elevation, pressure, and temperature. Now, objects, as opposed to fields, are phenomena that do not cover the total study area. And the space in between these objects is potentially empty or undetermined. So I'll skip to the next slide again and come back. So the different phenomena that we talked about happening in the scene, one phenomena could be the rocks. These are huge rocks on the seashore. But are they present throughout the study area? If this entire scene is my study area, are these rocks present everywhere? The answer is no. They are only present at certain places. What about the rest of the places? Are they there? The answer could be no, or it could be it has not been surveyed yet, or it has not been mapped yet. There could be smaller rocks which have not been mapped yet. So that is what the definition of geographic object states, that a phenomena which does not cover the total study area and the space in between these objects is potentially empty or undetermined. Examples could be buildings, rivers, anything. I mean, you think of any phenomena happening around you outside, let's say roads. Roads is also an object. They happen only at the places where they are. In the rest of the places, there could be buildings, parks, other stuff, lakes, but not roads. So yes, so you can think of any geographic phenomena in your mind and then question yourself whether that phenomena exists throughout the study area. So we will come across more examples of each of them. Let's take examples of objects. A good example is buildings or rocks in this case. They exist only where they are. In the rest of the places, it is either not there or potentially undetermined. If you look at this screenshot taken from the ISRO's geoportal, the Indian Space Research Organization has its own geoportal. The name of that geoportal is Bhuvan, Bhuvan, Bhuvan. You should visit this site. And on this site, you will find a lot of good information. So this is a screenshot of high resolution data on Bhuvan for a city in the southern part of India called Kochi in the state of Kerala. There they have this natural phenomena called backwaters. Now in this image, you can see roads, you can see some buildings, and you can also see some greenery, some vegetation. So in this example, buildings are objects because they have crisp boundaries. They exist only at certain places. In the rest of the places, they are not there. They could be water, they could be road, there could be vegetation. So characteristics of objects are that they have crisp boundaries, one, and second, that inside the boundary, there is only one value. Now, what do I mean by that? I mean, now, if I draw a rectangle around this building here, okay, may not be very visible, but if you look at this bottom tip of this image, there are some large buildings, and if I draw a rectangle around this building, so the building has crisp boundaries, and inside the boundary there is only one value. That means inside the boundary that I have just made, it is all building, it is not another class. Similarly, in this case, inside this black colored polygon, it is all rock and nothing else. Okay, so that is the definition or characteristics and examples of objects. Let us move to field. Examples you have seen: temperature, pressure, and elevation. Characteristic is that on the study area or on the image, you can measure the quantity or the phenomena everywhere. So for example, height can be measured everywhere. Fields are further subdivided into continuous and discrete. Continuous means that all changes in the field value are gradual. That means the change in the field value in the study area will happen slowly. For example, elevation. The elevation is increasing slowly if you go from this point in the image to this point in the image. And since it is a continuous change, it is a differentiable field. That means in mathematics, you can differentiate this value to create derivatives. In the example on right, we can measure the gradient or slope of the land as the change of elevation. You can measure the rise over the run, that is the increase in height with respect to the distance, and find the slope of the image, or slope of the study area. The second type of field is called discrete. discrete fields cut up the study spaces into subpaths with clear boundaries, with all locations in one part having the same value. Now look at the example on the right. You will see that we are trying to show the phenomena land cover. We want to see what is the natural cover of the land. So on the top part, there are bare lands. Then there is a clear boundary, and the bare lands then change to the agriculture in the valley. And after the valley ends and the slope starts, on the southern slopes you have shrubs. So if we talk about the geographic phenomena land cover, you can get a value at each and every point of the study area. That is, if I want what is the land cover at this point or this point or this point, any point in the study area, I will get a certain value. Hence, these are fields. And since the values change abruptly along a certain boundary, it is called a discrete field. In a continuous field, in the previous slide, the values change gradually. But the value is still available throughout the study area. Same in this case, the value is available throughout the study area, but the change is not gradual, the change is abrupt. What are other examples of discrete fields? It could be land classification like the one shown. It could be geological classes, types of rocks and stuff. Soil type, land use type, crop type, or natural vegetation types. These are different examples of discrete field. So far, we have only discussed geographic phenomena. In the following slides, we will discuss the computer representations. There are two types of computer representations. First is called tessellations. Going by the English word tessellation, basically means that you cut up the study area into equal bits, and for each bit and for each part you assign a certain value. This gives us what is known as the raster data model. The second type of computer representation is vector-based representation. That gives us the vector data model, and we'll see more in detail about both of them and how they link with geographic phenomena. Excuse me. So let's talk about regular tessellations. Why this word regular? Because there is something called irregular also. So we'll come to irregular tessellations in a bit. First, let's talk about regular tessellations. What is tessellation? Tessellation, as I told you, is dividing up the space or partitioning of the space into mutually exclusive cells. That means the value of one cell is independent of the value of the neighboring or any other cell. That together make up the complete study area. So if this picture here is the reality or the study area, and if we divide it into these grids, and then for each grid I want to assign a value which represents the majority phenomena happening on ground, this kind of representation is called regular tessellation, which also gives us the raster data model. In case of regular tessellation, the cells are of the same shape and size, and the field attribute value assigned to a cell is associated with the entire area occupied by the cell. That means if I say this cell on the top left is green, here representing forests, then the entire cell represents forest. It is the information that there could be smaller parts within the cell that have different land cover is lost. Okay. So for example, if you look at this white boxes here, they are meant to represent the road. But as you will see on reality, the road is a linear feature and it doesn't fit neatly into these square boxes. Okay. So that is one of the drawbacks, but the positive thing about this is you have a very easy way of representing what is happening in reality into a computer representation. The size of the area of a single raster cell represents what is known as the raster's resolution. So if one cell is 10 meters by 10 meters, then the area of the cell is 100 square meters, and each cell is identical in nature. No two cells can have different height and width for regular tessellations. Here it shows that if on ground there is so the colored image at the background tries to show what is there in the ground, and if it has in a single grid multiple phenomena happening, the value which is assigned represents the majority phenomena that is happening on ground. So let me zoom in here and try to show you what I'm trying to say. So here in this cell here, which says number 3, there are actually 3 phenomena which is happening inside the grid. There is a farm shown in this light yellow or brown color. Then there is a stream which is shown in the white color, and then there is forest or other vegetation shown in the green color. But within this cell, the majority of the area is occupied by the stream. Therefore, the value 3 is assigned on the cell. Same case here, the value 4 is assigned. In this cell, out of these 3 classes, the water body or the stream occupies the majority area, so 3 is assigned, and so on. So that is how it works. Now, by now you would have thought about this, that this representation depends a lot on the cell size, the size of the grids. The size of the grids not only dictate the geometric accuracy, but also the attribute accuracy of the feature. Now, what do I mean by geometric accuracy and attribute accuracy? So if you look at this image here and assume that this yellow color represents a field, agricultural field, and the rest of the white part is non-agriculture. I have only 2 classes, agriculture and non-agriculture. The area of this field, it comes to be 71 meters square. Now, when I divide the space into 1 meter by 1 meter cells, I get 16 by 16 cells. Out of these 16 by 16 cells, only 73 cells have the same value. That means the area of the polygon now stands at 73 meters square. Also, you would see that the shape of the feature has got distorted. It is now has a jagged line. The boundary is a jagged line. If you increase the cell size to 2 meters or 4 meters, you will see that there is more distortion in the area figure and there is more distortion in the shape of the farm itself. So if you have smaller cell sizes, you have higher resolution, you have higher feature spatial accuracy. That means the outline, the shape, the geometry of the feature is preserved, is more accurate. But because of smaller cell sizes, high resolution, the data size is more, the file size is larger, which then leads to slower display, slower processing, etc. because of its size. If you have larger cell sizes, you would have lower resolution, lower feature spatial accuracy, that is the geometry of the feature is less accurate, but it will have smaller file size. You only have to store 4 into 4, that is 16 cells. In this case, you have to store 16 into 16, that is 256 cells. So because of the smaller file size here, you have faster displays, faster processing, etc. As I told you, there is also something called irregular tessellations. Irregular tessellation, the definition is similar to the one before, except now that the cells can vary in size and shape. Irregular tessellations are again partitions of space into mutually exclusive cells, but now the cells vary in size and shape, allowing them to adapt to the spatial phenomena they represent. Now you need not divide the entire space in equal grids and in some cases keep repeating the information several times. In these representations, you can remove that data redundancy. So let's look at two examples quickly. First is called quad trees. A quad tree works like this. You have the entire study area, you divide it into 4 quadrants, and then you look at each quadrant. If it has homogeneous value, that is a single value, then you do not divide it further into 4 quadrants. If not, then it has to be further divided. So in the first quadrant here, or let's look at the fourth quadrant here, when the first division was done, there were all 3 classes. So further it was divided into 4. You see 2 cells were homogeneous. They did not have any other value except class 1. So these were not divided further. Then this cell here was divided further. Out of this, one cell had a value 1. The rest of them have mixed values, so they were further divided. And the process is continued till a certain threshold, that is, you have the minimum size of a cell, or you stop when all homogeneous cell blocks are created. The second one is called run length encoding. In this, a single value, a sort of a binary map can be stored. So here you see in row 1, only the 5th column has the value 1, has the value yellow, let's say. In row 2, you have the column 5 and 6, which have the value yellow. In row 3, it is 4, 5, 6, and so on. So this data can be represented as a row of numbers, which is called run length encoding. Now let's come to the vector-based representations. There are 3 types of vector-based representations: points, lines, and polygons. When you're working with (2D) coordinates, you only need to store x and y's. When you're working with 3D coordinates, you need to store x, y, and z. Points that are used to represent objects that are shape and sizeless or zero-dimensional. In this case, I would like to point that phenomena which are represented as points, quite a lot depends on what scale of map you are trying to make. So for example, if you're trying to make a national level map and you want to see all the cities, then it is very difficult to see the outline of each and every city. So how do you show the cities? Just as points. Similarly, if you're making a map of your town or your city and you want to show all the schools on them, there could be many schools. And not all the schools may have big boundaries, like big campuses. So they have to be shown as points. Then we come to lines. Lines are one-dimensional objects like roads, railways, railway tracks, canals, rivers, etc. A line is defined as 2 end nodes, that is the start node and the end node, and having 0 or n internal nodes. So a line must have a start and an end, and inside that there could be no nodes, no 0 internal nodes, or there could be n number of internal nodes. An internal node or a vertex is like a point that only serves to define that line. Now look at this image here. The top image shows a meandering river of sorts, a river which is changing its course. And if you digitize it, you keep one point here, another point here, then here, so on. If you roughly digitize it with the vertices at large distances, you will see that the shape of the actual river gets distorted. So how do you fix that? You increase the number of internal nodes or vertices. In some cases, it may be required to do the reverse. It may be required to do the reverse, that is, reduce the number of internal vertices. That thing is called generalization. When you want to zoom in and zoom out, when you want to zoom out, that is, reduce the amount of information on the map, then there are processes called map generalization, which systematically removes information from the map. One of the techniques involving reducing the number of internal vertices. A classical example could be the Douglas-Pecker algorithm, which does exactly this. It reduces the number of internal vertices. The third and the last type of computer representation is polygon, vector polygon. Here we show anything which can be enclosed within a polygon. These polygons are generally mutually non-overlapping. You wouldn't draw in normal circumstances polygons which overlap with each other. So if I had to map these vertices, if I had to map these warehouses, then I draw polygons around them. And when I remove this base map, this aerial image, then the output would appear like this. These are the 5 warehouses that I could see in this region. There is a third type of data model called triangulated irregular networks, or TIN, T-I-N, TIN. It is a vector-based representation of a surface commonly used in terrain applications. So things like making the digital elevation model or slope and aspect and things like that. So what is a TIN? So basically you have points, height points at different locations inside the study area. You use some method, example could be Delaunay's triangulation, to create non-overlapping triangles around these points. So join these 3 to create one triangle, these 3 to create one triangle, these 3 to create one triangle, and so on. So you create these triangles to cover the entire study area. After creating these triangles, you use an interpolation technique such as Thiessen polygons to construct the values at other places which are not known. The only known values are these points. At the other location where the value is not known, we use an interpolation technique. Some examples of TIN could be slope. So you see each triangle here is shown in a different color. These colors represent the slope of each part. Or example could be aspect. So this triangle here, which is shown in this light blue color, it represents south. The light green color here shows the southeast, and so on. Now let's try and link these two things that we talked about, the geographic phenomena and the computer representation. So how could geographic fields, for example, elevation, be represented? Do we need to represent it as rasters only? Or can we also use other computer representation like vectors or TIN to represent that? Let's see in the slide. So elevation could be shown as a digital elevation model. This is a raster data model. This is how it looks. This is how it looks. Here it shows the blue pixels shown with the blue color is having low elevations. The ones showing with yellow and orange have higher elevations. Elevation, the phenomena could be shown as contour lines, similar to your topographic sheets. Now these are lines, so they have to be vector lines. Or it could be shown as a TIN. We saw TIN can be used in terrain applications. Or it could be shown as point heights and so on. If you talk about discrete fields like land use or soil type, it can be represented both as vector polygon here or as raster. The only difference is if you look at the edges or the boundaries, you will see the vectors have a smoother boundary, whereas the rasters have a jagged boundary. That is not a smooth boundary. Same is the case with points and lines. They can be represented, or that is objects, they can be represented as both vectors and rasters. The only problem is that in rasters, the outline or the boundary is not very smooth as in case of vectors. Same is the case for lines. So it will be interesting to evaluate both these data models. In terms of data structure, rasters are very simple, whereas in comparison to that, vectors are a little complex. When you talk about overlaying these different data sets and doing calculations, rasters, it is very simple because it's just a matrix with some values, and overlaying values can be added, multiplied, and stuff like that. Whereas in vectors, it can be done, but difficult to perform. Compatibility to remote sensing imagery. All images that you get from satellite or airborne platforms are in raster data models. So yeah, it is compatible with RS imagery, whereas vector data is not directly compatible with RS imagery. When you talk about spatial variability, how the values are changing from one grid to the other, it is more efficiently shown in case of raster data models and insufficiently shown in vector data models. In case of programming, rasters are very simple. But when we talk about storage, rasters tend to store a lot of redundant data. So it is inefficient, whereas vectors are compact. Geometric properties are erroneous in case of rasters, whereas they are correct in vectors. When we talk about concepts like topology and network analysis, it's very difficult to implement on rasters, whereas in case of vectors, it is very easy and pre-built algorithms with efficient encoding. Finally, when we talk about map visual appeal, which kind of data model will make me the best looking maps? You will have to opt for vector data models, that is point, lines, and polygons. Raster data models will also make you maps, nice maps, but the vectors make more beautiful maps. Having confused you enough after talking about these different representations and phenomena, at the end of the day, which model is correct or which model is suitable for your application depends on two answers or two questions. Question one, what is the original raw data available in, or what format is it available in? If we talk about temperature measurements, for example, if you have data from weather stations, these are point data sets. If you have data from satellites, there are satellites which measure land surface temperature or air temperature, or some models which model or which predict the surface temperature. These are all rasters. So it depends on what is the original raw data available in. Second question would be, what sort of data manipulation would you like to perform? Would you like to do programming on them? Would you like to create your own algorithms? Rasters will be more easier. It can be done on vectors, but slightly difficult. Would you like to make maps just for visualization? Then vectors, not rasters. So depends. So final choice of representation depends on the answer to these two questions listed here. Also, to confuse you further, in all GIS softwares today, including the one which will be demonstrated to you, that is QGIS, there are options to convert from one data format to other. That is, you can convert from rasters to vectors and vice versa. But remember that each conversion adds some error to the data. That will possibly be covered in error propagation, one of the sessions on error handling and stuff. I also wanted to emphasize the importance of scale when it comes to representation. So for example, in these two images, I want to represent towns of India which have the population of 500 and more. So there are so many of them. And if I am making a small scale map, something like 1:10 million, where I can see the entire India in this 5 inches by 5 inches screen space, if you're watching on a mobile device, maybe even smaller, it is not physically possible to show the outlines of individual cities. And there would be so many overlapping cities also. So the only option is to show them as points. So in a small scale map, the phenomena you're trying to represent, let's say towns, then it would be a point map. Whereas the same phenomena on a larger scale map, for example, 1:50,000, here I can see the boundaries of individual villages and towns which surround the Dehradun city. So here I can show the towns as polygons and I don't need to stick to points. So the choice of representation quite often depends on the scale of the map. Also how the data is collected and also how or what kind of application you want to build on top of this. Last two slides. One is that all the data that we are collecting these days, some of them are in flat files, like you may have heard of the term ESRI shape files or GeoTIFF files or for example, Google Earth KML files and so on. These are called flat files. The data is there in a single or bunch of files. Some of your data could be in simple tabular manner. For example, in Excel spreadsheets, you could have name places and some data, or you could have lat long and some data. You could have some CAD drawings, some recordings on your GPS receiver, some data in your databases, or some data that can be consumed through a technology called Web Map Service. All these things can be integrated together inside GIS, specifically inside the open source software QGIS, which will be demonstrated to you in this course. So we will take a small break here. In the break, you could type your questions in the chat box, and you could also try to answer these yourselves. Don't put the answers on the chat box now. You just have to put a tick on whether these phenomena are fields or objects. And if it is a field, then whether it is continuous or discrete. And if it is an object, whether it is a point, line, or polygon. So you can fill the answers in your copy and you can put your doubts in the chat box. And we will discuss both the answers and your questions after a short break. Thank you.
That's it.
So welcome back, friends. I'm happy to see a lot of you are putting the answers on the GoToMeeting chat box and the e-class chat box. So let's go through the questions one by one, and then you can match your answers. I think it doesn't go one by one. Yeah. So the first question was elevation points. Now, we are, the phenomena we are trying to measure here is elevation, but the raw data, the input data is in form of points. So these elevation points can only be at discrete places, and it can be only represented as points. So the first answer is this is the phenomena is of type object, and the computer representation is of type vector point. Can somebody confirm if they are getting the audio?
Yes.
Are you able to hear? Okay.
Yes, sir. Yes.
Thank you. Thank you. So the next question is, how do we represent, or what is the type of phenomena of canals, water canals? And these are linear structures. These are definitely object, and they're of type line. Now the third one is slightly tricky. I specifically mentioned a large river. Something could be something like the Amazon or the Brahmaputra in India, which has a very wide width, a large river, and at a very small scale, at 1:5,000. Here you can see the outline of the river. So just by showing it as a line would not do justice to the representation of the large river. So this is of type object, but the representation should be polygon. Okay, let me just display all the answers. The representation should be polygon. Now, satellite images, for example, the Indian sensor list 3, which is at 24-meter spatial resolution. Now, what does the satellite image capture? It captures the energy which is coming from the ground, from Earth. And this data or this phenomena is happening throughout the surface of Earth, at each and every point on Earth. Each and every point on Earth is reflecting some energy back into the atmosphere, which then reaches the satellite, the sensor, and we get the satellite image. So the phenomena is definitely a field, and this radiance, the energy values are gradually changing. They don't change rapidly generally. This is a continuous field. A digital elevation model, or DEM, represents the elevation. We saw in multiple examples that it is a continuous field. A soil map is where you can show different types of soil. So loamy, clay, sandy, and so on. And you generally draw discrete boundaries around them. So this is a discrete field. Finally, the ward boundaries. This could be any kind of administrative boundary, a district, a state, a country. These are generally objects and represented as a vector polygon. Some of your answers may differ from mine and need not be incorrect. Okay, please understand these are subjective elevation. Obviously, anybody can say it is a field phenomena. Elevation points I generally wanted to refer to point-based collections, or you went at certain points in your study area and you collected the height. So your answers may differ, need not be incorrect. This is a very good discussion topic, and we can have different answers. Okay, I will next. I will take your questions that you have put in on our different platforms. But just in case, if you have any further questions at any point in time in future, you wish to contact me. This is my email address: prasun, prasun @iars.gov.in. You can contact me there. But I'm not leaving you guys right now. I will go through the questions right now. I'm going through the GoToMeeting chat box. I see mostly answers. There are two interesting questions. I'll take them. There's one is which says, are quad tree rasters integrated into QGIS? And what would be their best recommended use, analysis, or queries? Very interesting question. And That means that you were listening to the lecture and you're very interested in the subject. Thank you for the question. What Adrian is asking is, are quad tree rasters integrated into QGIS? So I showed you there are two types of tessellations, regular and irregular. Regulars are the ones which are generally used. Irregular tessellations were used in older systems when the computers were not very fast and softwares were not very user-friendly. In those days, different irregular tessellations were being experimented with. So quad tree, run length encoding, and other irregular tessellation techniques are more of a theoretical interest. They are more on for understanding what tessellations mean and what are the implications of regular and irregular. In QGIS, as far as I am aware, quad tree representations are not available. There are other kinds of new types of representations which are coming up. There's one representation called mesh layers, which could be used for flood routing and those kinds of applications. So there are newer things which are coming up. Quad trees, these are not available in modern day softwares and systems. In older systems, they were widely used because that time, like a 4 MB hard disk was a big deal. So you had to save the amount of data. So today we can have the luxury of having terabytes of hard disk on our personal computers. But I'm talking about like 3 or 4 decades back when computers were not personal. Your company or your college or your university had a computer and you had to use it on a time sharing basis and you could not eat up all the resources. So then you had to think of innovative ways of reducing the amount of data storage. And one way was to reduce the amount of data being stored redundantly. That one was quad trees and so on. So yeah, I don't know. I have not seen any application of quad trees in QGIS. If you have seen, if you have worked, I would be interested in knowing. You can send me an email and I would be very happy to connect with you. There's one more question by Adrian where he talks about hexagonal geometries. This is a very interesting question. Some companies like Google and Uber, they are experimenting with Uber, the ride sharing, the ride hailing app, and Google. You all guys know what are Google. So they are experimenting with newer types of data models, not only raster, vectors, and tins. There is a paper by Google in which they talk about a data model called S2 geometry. S as in Sweden, S the number 2, S2 geometry, where they talk about dividing the earth into hexagons and having pyramids of hexagons. So they have the whole world divided into 6 and then each hexagon then further divided into 6 and so on till you can reach down to individual houses, individual points on the road. So that kind of pyramidal structure. And they have had a very claim to have good success in high usage application like Uber app and all this. And they are also doing a lot of analysis like mobility, how are people moving throughout the day, which are the places where they reside, which are the places where they go to work or to study or to play, or where are the places they like to hang out in the evening. So that kind of human mobility analysis. So yeah, these are new types of data models which are being experimented by different companies. Uh, but I have not seen any such application on QGIS. Uh, but I would be really interested in working with those. So yeah, currently we work with uh, most of the work that is done today, most of the work throughout the research and academia in the world is mostly on rasters and vectors and tins. And then there are certain companies which are doing some innovative stuff, which maybe we will migrate to in some point in the future. Let's
Yeah, you can type the question here also in GoToMeeting. Sorry, in Microsoft Teams if you are still having the any doubt. If you are having any doubt related to geographical phenomena example, you can type here in the chat box, whichever chat box you see, or you can turn on your mic and ask the questions. So since this course is streamed on various platforms, not only on Microsoft Teams, so you may hear the instructor is saying something, you can post question on that platform, but whichever platform is accessible to you, you type that your question there, it will reach us. So in case there are no questions, we can end the class now and we'll meet tomorrow with lecture on someone is asking which software India is using to analyze GIS data. Not only India, across the world, ArcGIS and QGIS softwares are popular GIS software. They are widely used. So earlier ArcGIS was more preferred, but nowadays QGIS is name of the software. Uh, it is having capabilities similar to ArcGIS, but QGIS is free and open source software. You can visit the website, just search QGIS on Google and you will get QGIS website. It is freely downloadable and you will find for practical exercise, preferably you can download the latest version, which will be 3.2 something, 3.2.x. And I request team to stop sharing the screen. EduSet team to stop sharing your screen. So you can download the latest version, which will be 3.2x. So even if you are having 3.2 or 3.16, so basically version 3.x is suitable for the demonstration which will be given in this course. Actually, you will find QGIS 2.x that is not suitable for our practical demonstration. So you can download latest version if you have good access to the internet, or if you are having already QGIS, some version of QGIS, then you can make sure it is QGIS 3.x. We will use QGIS. Anything else remaining? Any doubt? Okay, then we'll meet tomorrow. Thank you for your attention. Yes, there will be classes. So tomorrow is a holiday. Classes will be on day after tomorrow. On October 6th, there will be classes from 2:30 IST. Yes, tomorrow is public holiday. Day after tomorrow there will be classes. Next class will be on October 6th at 2:30 p.m. IST. Okay, thank you for your
Thank you.
attention. We'll meet after day after tomorrow on October 6th. Thank you.
Thank you.
Thank you.
مايشينا 12 سو مايشينا تخرجوا 12 الوحدة. هنا جامدين. ماشي اليوم مش عارفين والو هذا. وين تاكي والله مليش ناس لا ما تهضر مليت